Let us see how will it look in terms of a block diagram. So we will take first stage where interpolation takes place by I1, and the output will go through anti-imaging filter with response H1n. So this becomes my first stage interpolator. Let me now give it to the second stage I2, and output of second interpolator goes through a filter, anti-imaging filter with impulse response H2n. So this obviously becomes second stage of interpolator. And likewise, I can have multiple stages implemented. So we can show the last stage directly now. The final interpolation will be IL, because capital L is the total number of stages, and the corresponding filter, let's say, has the impulse response HLN. And output of that will be my final output Y of n. So when we start with an input X of n with sampling rate, let's say fx, what you think will be the sampling rate at the first stage? It will be nothing but I1 times fx. Sampling rate at the second stage will be nothing but I1 into I2 times fx, because I1 and I2 will multiply. And likewise, when you reach to the last stage of interpolator, this stage rate will be nothing but I1 into I2 into IL times fx. So finally Fy will be, and this whole product of I1, I2, I3 up to IL is nothing but my overall interpolation factor. So we will achieve the sampling rate conversion by capital I. So this is nothing but stage number 1, this is stage number 2, and likewise this will be stage number L. So here L shows the number of stages. So you can see that there are L stages of interpolation and filtering. Please note that the filter in each of the interpolators eliminates the images introduced by the upsampling process in that corresponding interpolator. So we will need L filters in the implementation of L stages. So exactly same can now be done for decimation. So let us take decimation by a factor capital D, where D may be factored into a product of positive integers, which can be written as pi di. Pi stands for the product. I will vary from 1 to L again. And this can be implemented as a cascade of, let me use a different notation for the number of stages just to have a general case. So let's say now we go up to J number of stages. So this can be implemented as a cascade of J stages of filtering and decimation. So I can have a similar figure that we have drawn for interpolation. I can have exactly same figure for decimation, with a small difference that in this case the filter will appear before decimator block. So this is how the overall block diagram will look like. You can see that this H1n and first interpolator, they will form stage number 1. H2n and the second decimator, I'm sorry, this is a decimator here, will form stage number 2, and the final stage will be again a last filter and decimator block. So this will be stage number J. If you write down the sampling rates on each and every point, X of n has the sampling rate of fx. At the intermediate point, the sampling rate will be fx by d1. Here it will be fx by d1, d2. And likewise, the last sampling rate will be fx upon d1, d2, dj. And this is nothing but, this whole product is nothing but capital D, the original decimation factor. So Fy will simply be fx upon capital D. So this is what we will achieve through the multi-stage decimation process. So to ensure that no aliasing occurs in the overall decimation process, we can design each filter stage to avoid aliasing within the frequency band of interest. So each stage will have its own anti-aliasing filter. So now on this whole thing, multi-stage implementation of sampling rate conversion, there can be a small theory question, where you have to explain the concept of multi-stage implementation, and you have to draw these two diagrams and explain how interpolation and decimation will be carried out. Now there can also be numericals based on this multi-stage implementation. So let's go through few important numericals that can be asked.